Hi, everybody. We're going to do another time series topic here in Stata, this time looking at the Chow structural breakpoint test. So I've got some data here to play around with. It's the daily return on Apple stock and the daily S&P return. So we're playing around with a little capital asset pricing model type equation. So let's just kind of bring up a regression just to have a starting point here. So we're going to regress the return on Apple as a function of the market return, which again is being played by the S&P daily return. And we get a positive significant coefficient, a little bit over 1. And we would say, okay, that seems reasonable, right? However, what we want to do is know what to look for to get evidence of whether or not there is some degree of instability in those coefficients. Here, we're only looking at the intercept and the slope. More generally, right? If we had a larger model, we could be looking at changes in any of those marginal effects within our time series sample. Right? So thinking about a case like this, right, where if we have a set of observations, we fit a linear model to it, that looks fine, but could we do better by splitting up that model, essentially, fitting two separate subsamples? Realistically, what we're saying is, could we do better by allowing the intercept and slope parameters to change at some point in our sample, right? So if that is the case, then our model, our sample, suffers from a so-called structural break. We want to know how to test for that and account for it, okay? So just to get kind of a visual here for our little example, if we just brought up a scatter plot, right, between our y variable Apple return and our x variable market return, nothing seems to be amiss here. In fact, that looks like a almost perfectly linear relationship. So where might we look for evidence of instability? Well, one thing we could do is look at the underlying data, right? Always get a visual. So if we did a time series plot on that Apple return, so just use the TS line command in Stata, here is a little bit of evidence, right? So we have a pretty stable return here between, negative 3%, positive 3%, and then around about observation 100, things start to change. We get this kind of sustained increase in volatility for the rest of the sample. Does that represent a structural break? Do things change at that observation 100 point? Since this is a return, we could also look at the price level, right? So here, this is the adjusted close. And by the way, I'll put the kind of the do file, the commands to get this data in the description so you can play along as well. And here we see what's happening. So this is the price per share of Apple over the last year. And of course, we had the market downturn when we saw the shutdown due to coronavirus. And then we see a pretty stable upward trend after that. So basically a little blip and then a trend. Well, that's going to introduce a lot of volatility. Could it also introduce a structural break, right? So what we could do, again, just to kind of get the visual of it again, is we can kind of plot the best fit regression line for the observations before our potential breakpoint observation 100 here in the little example versus after it. So we can use the two-way command in Stata. So we'll do the two-way and the linear fit between our y variable and our x variable. If our time indicator is less than 100, and then do the same thing, I'll fit Apple return, market return if time is greater than or equal to 100. And this is what we are kind of thinking about, right? Here, that little blue line in the middle, that is the pre-break combination of points, right? That was when we had much smaller volatility. Remember, all the observations were between about negative 3% and positive 3%. The same thing was happening in the market as a whole. Then after that observation 100, the market went down, Apple stock went down, volatility increased, and then we get that red line, the best fit for the remainder of the sample. Well, so the question is this little pivot in that regression line for the first 100 observations, is that enough to be able to say we have a significant structural break, and that's something we would want to take advantage of, essentially, or include in our model? Well, that is where the Chow structural breakpoint test comes in. It's one thing to get the visual, to look at the behavior over time, look at the best fit lines, essentially the functions over different subsamples, but we need to turn this into a statistical test, right? So the Chow breakpoint test, luckily, is going to use kind of all familiar ingredients. We can really think of it as just a reconfiguration of our familiar F-statistic, F-test used for joint significance testing. Remember, with an F-test applied for a joint significance test, what we're thinking of is running a comparison between two models, an unrestricted model that contains all of the variables that we're considering versus a restricted model, right, where we have imposed the null hypothesis. We've set our suspicious coefficients equal to 0. We've removed those variables. Well, here, the role of restricted versus unrestricted is going to be played by allowing the break versus not allowing the break. And then we're just going to ask, okay, does that difference in the performance of the model under those two circumstances come out as significant? That's the trick, is putting that comparison into a statistic following a known distribution with critical values, and that's going to be our F statistic. Right, so the logic is, if there is no structural break, if it doesn't really matter if you're before observation 100 or after, well then, the sum of squared residuals, the RSS of the model, the performance of the model, is not going to change whether or not we allow there to be a break or not, right? Because if we allow the flexibility, well, then the best fit isn't going to change, so the errors aren't going to be changing much. So the comparison here is going to be between, again, the restricted and the unrestricted model. That's where we have to kind of really think about what we're doing in terms of mapping this idea of the structural break test to our more familiar F statistic formulation. But here's the way we want to think about it, right? We've essentially constructed 3 separate samples, right? The full sample over T observations, right, is kind of not taking into consideration a potential break. And then we have a pre-break sample that we'll call the T1 observations up to the break, and then some number of observations after the break, T2. So again, 3 subsamples that we want to use in this comparison: the before, the after, and the full regression. So back to that idea of mapping the structural break approach to the familiar joint significance F statistic, playing the role of the unrestricted model, right, is going to be the sum of squared residuals across the 2 subsamples, right? So the unrestricted model is when we allow the break to occur. We let the intercept and the slope change within our full sample. The vocabulary is not obvious necessarily. The way I think about it is that we are not restricting our model, right, to have a single slope and a single intercept. It's unrestricted in that sense. The more useful way to think about it, I think, is that allowing that break, even if it's not significant, is always going to make the model perform a little bit better, right? Giving a little flexibility will reduce those errors a little bit, and it should be the case that the unrestricted sum of squares is always smaller than the restricted, right? So we basically run the same regression over the pre-break sample, run it again over the post-break sample, extract the sum of squares from each, add them together, and that's going to be that RSSU in our F statistic calculation. Okay. So playing the role of the restricted model then is the model with only a single intercept and slope, no flexibility, no break is allowed, that's the full sample. So over the full T observations is going to be estimated. So essentially on the left here, it's stated when I ran the little CAPM example equation over the full sample, a little over a year, 274 observations, that is now the restricted model in our calculations here. What I haven't done yet is run the individual samples. We saw the picture of the linear fit before observation 100, pre-break, and after observation 100, but we haven't run the regressions yet. Okay. So now we've got all the ingredients for our Chow F-statistic, and it's going to look something like this. And the kind of the key component of it is going to be this numerator term, right? The difference between the sum of squares under the case of no break versus with a break. So the RSS that we see in that numerator term, that is the full model estimation. That is the restricted model sum of squared residuals. And then the sum in the parentheses, RSS1 plus RSS2, that combination is the unrestricted model. We divide that by the number of restrictions, right, which is going to be K, the total number of coefficients estimated, including the intercept, right? Because the idea of a structural break is kind of all bets are off. All of the slope terms and the intercept could be changing when we hit that break point. Okay. And also note that the specification of the model has to be the same throughout, right? So we have to have the same X variables, pre-break, post-break, and full sample. And then in the denominator term, we again have that unrestricted sum of squares, RSS1 plus RSS2, divided by what we would normally see as n minus k minus 1. Here is t minus 2k. So again, that big T is the total sample size, the number of observations in the full sample. So in our example here, that's the 274. And then 2 times k is twice the total number of coefficients estimated. The idea being, in order to get the unrestricted model, we had to estimate the model twice. So we have to account for that as a kind of a penalty in our degree of freedom calculation. And again, k includes the intercept. Okay, so with all that in mind, let's go ahead and, oh no, sorry. Before we do that, let's remind ourselves what we will do with that information, right? So what we do, we run the models, we calculate the F-statistic, and what are we doing? We're testing the null hypothesis that there are no structural breaks, right? Testing the null of stability. So if that F-statistic is small, then what that tells us is it doesn't really make any difference if we allow the break or not. So a break isn't going to be useful. And therefore, we would not reject that null. If the F-stat is large enough, well, then allowing the break does cause a big difference in the performance of the model. We would reject that null and conclude that the coefficients do differ across the sample, that there is at least one break within our sample. And that's where we get our conclusion. If our Chow F-statistic is greater than that critical value at a reasonable level of significance, say 5%, and the correct degrees of freedom, reject the null, conclude that, yes, we do have a structural break at the point tested. Okay. One other option we could do here, once we see it, you'll say, why would we ever do the way we just talked about? But it's good to know both. There's the so-called Chow regression-based test, which allows us to more directly test what we're really asking here, right? Basically what we're asking is, does the intercept of the model change pre-break versus post-break? Is there an intercept shifting effect? At the same time, we're asking, is there a change in the slope pre-break versus post-break? Do the marginal effects change? Well, basically what we're asking is there a significant dummy variable coefficient and a significant slope dummy coefficient? Are those two things jointly significant? That's all we have to do, right? So we would create a dummy variable that takes on the value 1 if we are after the break, 0 before the break. Then we would interact that dummy variable with all of our x variables. Again, my example here just has one x variable, but we would do it for everything in the equation. And then we would test the joint significance of all of those terms, the dummy and all of the slope dummies. And if we can reject the null that those coefficients are 0, well, that tells us the same thing that we just found, right? That yes, there is a significant structural break. The intercept, some combination of the intercept and at least one of those slope dummy terms do change at that breakpoint. Okay, so let's take a look at our example once again. So we know what we got to do, right? We got to go back and rerun that same equation, bring up our regression line here, pre-break. So we go if t less than 100, and we jot down this number. So that is the RSS1, the pre-break sample. Do it again for time greater than or equal to 100, post-break. Here is the RSS2, and then we also had the restricted model RSS from the full sample. Okay, so we wrote all those things down. We got this. We go to our F formula yet again, and we get our full sample value here, the 0.0627, so that's what we get here, minus the sum of the 0.0071, that's the RSS1, plus, scroll down, the 0.0544, the RSS2, there, divided by 2, right? Because we just had one intercept and one slope, all divided by the same sum here, RSS1 plus RSS2, over n minus 2k. So here, 274 minus 4. We do some calculations, and we come up with a value of 2.59. Okay, so what does that mean? We swing to the back of our Econometrics textbook, and we look up the 5% critical value with 2 degrees of freedom in the numerator, 270 in the denominator. It's about a 3.0. So we, in fact, do not surpass the critical value at 5%. We do not reject the null, and we conclude there is no significant break at that point of 100. So let's be very clear about this, right? This is kind of the downfall of the Chow approach to breakpoint testing is I just tested 1 point. All that means is the 1 point that I tested wasn't significant. Doesn't mean there if I tested it at observation 98 or observation 102 or anywhere else in the sample that I wouldn't find a break. It doesn't mean that at all. All we're saying is, okay, the 1 point I picked out with a kind of very cursory visual analysis was not, in fact, a significant break. Let's just real quickly look at how to do it really the easier way, right, by generating that dummy variable. So let's generate a dummy variable called break that takes on the value 1 if we are after our breakpoint, right? So we called observation 100 our breakpoint. So we'll say t greater than 100. Let's make sure that matches up. So, okay, so for the first sample, we went up to observation 99. So maybe we should actually go t greater than 99 to make it match up exactly right, because that'll start at 100 and go for it. That makes sense. Then we'll generate the interaction term. We could use the interaction operator within the Stata regression command. It's a little bit more difficult to call that up in a joint significance test. So I'll go ahead and generate a variable, call it break x. It's going to be the interaction between our break dummy variable and our lone x variable here. Again, you would want to do this with every explanatory variable in your regression. So here we'll take the product of the break dummy variable and the market return RM. Go back and run the same regression. As a function of the market return, we add in the intercept shifting effect, pre-break, post-break, whichever direction that goes, and our interaction term, break x, and we don't adjust the sample, right? So this is over the full sample, and we're looking for any significance here. in the dummy variable and or the slope dummy. So it looks like the slope dummy is significant at 5% based on the t-value. The intercept shifting effect, not significant, but let's put it into the F-statistic calculation here. So we'll test break and break X, and lo and behold, we get exactly the same F-statistic the way we did it here, calculating kind of the by hand way, and we get the same result, that we do not reject at the 5% level, that p-value above 0.05, we do reject at 10%. So we're kind of at a moderate level of a structural break. So lots of other things to consider here, but there's a walkthrough of how to conduct, 2 ways to conduct the Chow breakpoint test. Let me also mention that there is a third way of doing this in Stata. There is what's called the sbknown command that doesn't do exactly what we're doing here. It constructs a walled statistic version of a structural break test, which you may not have covered as a test statistic at the introductory econometrics level. So that's why I'm not including it here. I may run that as a separate tutorial later, but you may, if you do a Google search for breakpoint test in Stata, you'll see that as one of the options. This is a good way to do it by hand. You can see exactly what you're doing, and hopefully you found it helpful. So thanks a lot, and we'll see you next time.